Vector and scalar is a really important discussion within physics, and we need to make sure we understand the mathematics behind it and what they actually mean. So there's a very huge difference here, ladies and gents, and you can see vectors not only have magnitude, but they also have direction. And that is the real difference here, ladies and gents. Magnitude and direction. So what does that look like? When we are drawing vectors on a graph, we draw them in the form of an arrow. Because they have direction, we show which way they are going. So we have the tail of a vector and the head of a vector, all right? This shows us the direction that it's going. The length of the arrow is proportional to the magnitude. So what does vector versus scalar mean in physics? You've actually probably used this language and you weren't even really aware of it. When we talk about things like length, volume, mass, pressure, we don't talk about them traveling somewhere. They don't go anywhere. They don't have a direction, okay? They are scalar quantities, okay? When we do talk about things like velocity and acceleration and momentum and force, even when you speak about them, you say that they are going in a specific direction, right? So we even notify or we talk about this idea of vector versus scalar even in our language. But these are some basic units right here, ladies and gents, that we use for both vectors and scalars. You'll even see that some of them kind of have, like they're repeated, right? There's one on each side. So for example, you could say that length and displacement are kind of the same thing, right? Length is a measurement of from one place to another place. Well, displacement is kind of the same thing, right? You displaced yourself to go somewhere else. But there's a very distinct difference. You'll also notice that we have velocity and speed. Don't those two things have the same unit? Aren't they really the same thing? Well, no, they're not, ladies and gents. And that's what we're going to talk about right now. So what I want to do here, ladies and gents, is I want to make a little Venn diagram, and we're going to use distance versus displacement, or length versus displacement as our sort of Venn diagram topics. So the one thing we want to talk about right away is what they have in common. We both know that they use the unit of meters. That's cool. We both know that they go from like spot A to spot B. Okay, that's all right. It's a little general, but we can work with that. So what's the difference between these two things? Well, distance, ladies and gents, if I wanted to go from spot A to spot B, distance is the path that we travel to get from A to B, right? Displacement, ladies and gents, is a little bit different. Displacement is the idea that even though you did all this other stuff, even though you walked all the way around, in reality, you really only went from A to B. And this is the difference. This is displacement versus distance. Displacement is not the path that you travel. It is a straight line point from A to B. We're not talking about all the loops that you went. What is the straight line point from A to B? That is your total displacement. It is not the journey. It's the final destination, especially when we're talking about this. So scalar math is a really simple idea. We just add quantities together because there is no direction. We have nothing to really take into consideration. We can use them as we see fit. But vectors are a little bit different. Vectors, if direction matters, just like on a number line, you're going to have positive and negative values. Okay, there are vectors that can work against each other and they can cancel each other out. So you can have two vectors that build onto each other to create a stronger vector, two forces that line up to push even harder on an object. You can also have two forces or two things that counteract against each other. They're going to make the total force on the object less. And this works in all directions. It works in the x-axis, it works in the y-axis. If they are going in the same direction, they add on to each other. If they're going in opposite directions, they cancel each other out. It's not until we start getting two-dimensional vectors that things get a little bit more complicated. Now this, ladies and gents, is where I really want you to start paying attention, because we will be using geometry or geometric math quite a bit when it comes to vectors. This is one of the huge skills that IB physics and physics in general is based off for Newtonian kinematics. When we look at a vector, whether it's velocity, force, displacement, no matter what it is, a vector is always drawn with an angle, okay? Now you'll notice here that we can break this vector into two components, what they call a cosine theta and a sine theta. A cosine theta is next to the angle, a sine theta is not next to the angle. Now it's a little complicated, and you'll notice I've put a picture of a right triangle next to this vector. There's a very specific reason for that. Because this a sine value, I like to draw it right over here at the end of this vector here. Now what this shows us, ladies and gents, is that our sine value, our a sine of theta, completes the triangle. So how do we break down vectors? When we are presented with this information, how do I find the x component or the y component? Ladies and gents, that's what we like to call a cosine theta and a sine theta. This is the x component of the vector. This is the y component of the vector. How do we solve for these two things? We use geometry, ladies and gents. We use right triangles and we solve. Okay, so geometric identities are going to be very, very important. Now you're probably going, oh, I don't remember geometric identities. It's cool. Don't worry, I got you covered. These are your geometric identities. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. If you can't remember that, ladies and gents, remember the age-old adage of so ka toa. Okay, easy way for you to remember your geometric identities, and you can always break down a vector using this. Okay, it will get more and more complicated as we move through, ladies and gents, but we have to remember that when it comes to vectors, right, vector math is all about geometry. Your goal is to always find, oops, not the square, the right triangle. That's a pun. Remember that. So, real quick, ladies and gents, I want to give you a nice example, all right? So if I have a vector that is going up at, let's say, 30 degrees, and this vector has a magnitude of 17 newtons, all right? So we have a force. Let's say we kicked a soccer ball with 17 newtons, and boom, it's off, all right? Now, what are the components of this force? Let's see. If we wanted to break it down, we would have to find the y component, and we would have to find the x component, if I could spell. Breaking this down is really simple. We know the hypotenuse, we know the angle. And ladies and gents, to set this up, we just have to use our trigonometric identities. So cosine of theta is equal to adjacent over hypotenuse. By adjacent, what we really mean, ladies and gents, is next to the angle. It is adjacent to the angle. So cosine is going to be equal to our x component, divided by the hypotenuse, 17. Solve this, 17 times the cosine of 30 degrees is equal to x. Boom, you now have a numerical value in newtons, right? Because this is a measurement for force of measurement. You now have a value in newtons for the x component of this force. You can do the exact same thing for the y force, okay? So we can say that we know this is going to be sine of 30 degrees is equal to opposite over adjacent. I'm going to call it y over 17 newtons. 17 times the sine of 30 degrees is going to give you your y component. That's all it takes, ladies and gents. Lots of questions will strictly ask you, if this object experiences a force at 30 degrees, what is the vertical component of the force? What is the y component of the force? We've got to be able to break them down. As we go through some of these contents, we'll start to understand that there's a very unique relationship between these two things. There is none. They don't affect each other. Components in the y direction do not affect components in the x, and vice versa. So there is a reason for us to break these things apart. We have to explore them separately mathematically. So let's start talking about the next step, right? We know a little bit about vectors. We can break a vector down, but now how do we add two of these vectors together, right? They're at angles. How do we add these things together? So we always have to remember the number one rule of adding vectors. You always add vectors head to tail. Okay, that is absolutely essential, and you're going to see an example of that in the next page right here. So you can see this beautiful graph of two vectors. We have vector A and vector B. Okay, they've both been drawn from the origin, and you can see your x and y components, right? Each of them has been listed with x and y components, A1, A2, B1, and B2. All right, so here's your two x components. Here's your two y components. What's the next step here? Well, you can see that they've taken A plus B and they've added them head to tail. Really, really important here, ladies and gents. Now, I want to point something out, that when they did add these vectors together, you'll notice that what they did is at the end of vector A, they pretty much created a new coordinate system, and they copied and pasted B right there, okay? So this angle that exists from B, right, still exists right here. They've just copied and pasted that vector to a slightly different place. Head to tail, A plus B. Now, they've drawn the vector from the beginning of A to the end of B. This right here, ladies and gents, A plus B, is what we call the resultant. And I really need you to be familiar with this word, ladies and gents. The IB loves to use that term resultant. So make sure we're familiar with what they mean when we say that. It is the sum of our two vectors. Now, how do we get to this, ladies and gents? This is a rather complicated process right here, right? I mean, it seems a little unrelated to what we've talked about before. So let me break this down for you and show you how you can do the math of a problem like this. So let's talk about the best way to add vectors, ladies and gents. It's actually a lot easier than you think, okay? So what we're gonna do here, ladies and gents, is we're gonna take each vector. Here's vector A, here's vector B, here's our resultant. And what I'm gonna do is I'm gonna make a little chart here. Boom, just like that. For each of these, I'm gonna write down my X component, and I'm gonna write down my Y component. If I want to add them together, boom. All I have to do is add them together. So we can break these things down, ladies and gents. So if you wanted to, do it the way they have it here, very graphical, very easy, you could always do something like, oh, this is A1, A2, this is B1, this is B2. Here you're going to have A1 plus B1. Here you'll have A2 plus B2. But let's face it, life is just not that clean and simple, is it, folks? So we're going to have to do something a little bit different, all right? What I'm going to do, ladies and gents, is I'm going to assign a random angle here, okay? I'm going to say that this is 15 degrees, and I'm going to say that B is, let's say, 60 degrees, something along those lines. So now I have some actual numbers to work with, all right? I'm going to keep the magnitude as just A and B. So what we have to do now, ladies and gents, now we actually have to sit down and we need to break our vectors down independently. Okay, so here I have AY and AX. X and Y components for each vector, right? And I can break these down using my trigonometric identities. AY, all right, we use sine of 15 is equal to AY over A. A times the sine of 15 is equal to our Y component. We do the exact same thing with X, only with cosine. Cosine of 15 is equal to AX over A. A times the cosine of 15 is equal to AX. Now that I have these two values here, ladies and gents, I can actually plug them in. I can say that, hey, my Y value here is going to be A sine of 15. This is going to be A cosine of 15. Now we do the exact same thing with our B components. All right, so B is a little bit steeper. Here's B, BY, BX. We know that this is an angle of 60 degrees. So now we have sine of 60. And we can do the exact same thing for our X component with cosine. And once you have them, ladies and gents, you're ready. How do you find the resultant? How do you find these? All you have to do is add them together. It's one of the easiest things we can do. We know that our X components are going to be A cosine of 15 plus B cosine of 60. Here for our Y components, A sine of 15 plus B cosine of 60. We have found our X and Y values. Now, the last thing that I forgot to mention earlier, and I'm going to go up and add it to the video, is how do we now find the magnitude? You have your X and Y components, but how do you find the magnitude? So now that we've broken that vector down and we've added our components together, we have to find our magnitude, right? What is the length of this vector A plus B? It's actually really easy to find, ladies and gents, and it's probably the one equation you'll never forget. We know that all right triangles are equal to A squared plus B squared is equal to C squared. Well, guess what, ladies and gents? You know what your B value is. You know what your A value is. You have those things. All you have to do is plug them in to find your value of C, the magnitude of your hypotenuse. So in this case, ladies and gents, C is equal to A plus B, right? A squared is going to be your X components. B is going to be your Y components. Square root of A squared plus B squared is equal to C. So vectors in general, ladies and gents, it can be a complicated process. We will be taking it one step at a time, but please make sure you review those geometric identities. We'll be doing it in class as well. Here, ladies and gents, pause your screen, unpause it in a second, and you'll see the answers.